So I'd like to finish section 1.3 by talking a little bit about sets of numbers and how we classify numbers or how we organize numbers. So just the same way that a biologist organizes living things according to species and genus and family and so on, a geologist would classify rocks or organize rocks as igneous or sedimentary or metamorphic. Or something more mundane, in your closet, you organize your clothes. You put your pants on one side and your shirts on the other, and maybe your socks in a drawer. So too, we want to organize or classify all of the numbers that we've learned about. And so let's go through sets of numbers that we have learned that we've learned about. So the first set of numbers is accounting numbers. Those are the ones you learned as a very small child. They're also called natural numbers, and they just go 1, 2, 3, 4, and so on. And the next set of numbers is a set of whole numbers, and it's the same as the counting numbers, except for one difference. The number 0 is now included. And the next set of numbers is the set of integers. And at this point, we're introducing negative numbers. So we have 0, 1, 2, 3, 4, 5, 6, 7, and so on. And we also have -1 and -2 and -3 and all the numbers before it in the list. Set of rational numbers is a little bit harder to list out. The set of rational numbers is all of the numbers that can be written as a fraction. And so you could think of any integer, for example, 3. 3 is a rational number because it can be written as 3/1. You could also think of a number like 1/2 or 2/3, or you could also think of some decimals. You could think of a decimal like 0.9, which can be rewritten as 9/10. And so we said that rational numbers are numbers that can be written as fractions. And so what numbers can't be written as fractions? Well, those would be the irrational numbers. And let's see. If we back up for just a minute, let's take the fraction 1/3 and let's rewrite it as 0.3 repeating. So an alternate definition for rational number is a decimal that either terminates or repeats. So 3 is a terminating decimal. There's the decimal point right after the 3 that we don't write, and then you could put some zeros after that if you were so inclined. So 1/2 is a terminating decimal. 0.5 is its equivalent. Same with 9/10, terminating decimal 0.9, and then the repeating decimal is an example like the fraction 1/3, which is 0.3 repeating. So an irrational number then would be a number that's not rational. That would be a number that's a decimal that doesn't repeat or terminate. Decimal that doesn't repeat or terminate, or its equivalent. And so the first thing you would think of for an irrational number would be a number like the square root of 2, which is approximately 1.414, but that decimal goes on forever. Again, not repeating. You could also think of the square root of 3, which is about 1.7. And then what about the square root of 4? Well, square root of 4 can be simplified as 2. So 2 does terminate, and so square root of 4 equals 2 is a rational number, and it also happens to be an integer and a whole number and a counting number. And so then so radical, square root 2, square root 3 are good examples of irrational numbers. There are a couple more famous irrational numbers. The number pi and the number e are 2 more irrational numbers. And then that takes care of the irrational numbers. And then what are the real numbers? The real numbers are the set of all the rationals and all the irrationals put together, taken together. And I won't try to write that out, but I've just said it. And then, of course, the last set of numbers is a set of complex numbers, and I won't write that at the moment, but I'll write it out in a few minutes. So now that we have an idea about these sets of numbers, let's look at a diagram of how they all fit together. Start with the counting numbers. And we'll put a box around counting numbers to indicate that all of the numbers that fit that definition, that fit that list, would go inside this box. And then the next set of numbers is the set of whole numbers. It includes all of the counting numbers plus the one extra number plus the number 0. And so when we want to show the whole numbers, we'll put that box so that it includes the box of counting numbers plus the extra number, the number 0, that would fit outside of the counting numbers but inside the box of whole numbers. And then a similar idea for the integers. All of the whole numbers are integers, and then the integers also include some extra numbers, that being the negative integers. And so the box for integers would include all of the whole numbers plus the negative integers, -1, -2, -3, and so on. Now, we said a few minutes ago that the rational numbers include all of the integers. That is, every integer is a rational number. And so when we're drawing a box for the set of rationals, then it should include all of the numbers that we've already talked about, plus some more. And of course, the extra numbers now are numbers like 1/2 and 0.9 and 1/3. And then we come to the set of irrational numbers. Do the irrational numbers include all of the rational numbers? No, they don't. The irrationals now are a separate group. And so then they go alongside the set of rationals, but not including the set of rationals. And then when we put all of the rationals together and all of the irrationals together, then we have the set of real numbers. And I won't draw a new box for that because the box is already drawn, right? It's all of the rationals and all of the irrationals together. And so then we have one more set to go, and that's the set of complex numbers. And so complex numbers, let's see, I'm not sure if I've said it recently. I think I said it at the beginning of this section. Complex numbers include all of the real numbers. Every real number is a complex number. Remember, a complex number is any number that can be written in the form a plus bi. That box did not work very well, so let's leave it just like that. Okay, so then the set of complex numbers includes all of the real numbers. Remember, the complex numbers are numbers that can be written in the form a plus bi, and so we could take any real number from an irrational all the way down to a counting number, for example, the number 3, and we could write it in the form 3 plus 0i and convince ourselves that it is a complex number. So yeah, this is a lot to think about, but it's really a nice idea, and it's sort of the culmination of a lot of time spent studying numbers over a lot of years. And so how the sets of numbers are related to each other is real important. And then knowing the vocabulary for what each set of numbers means is very important, because sometimes we're told to solve an equation over the set of real numbers, or sometimes we're told to solve an equation over the set of complex numbers, or sometimes we're told to think of integers. Or sometimes, or for example, later in this chapter, we're going to study rational equations. Well, if you know what a rational number is, then you'll have a better chance to understand what a rational equation is. So, some vocabulary and a few things to think about here at the end of the section. That's all for 1.3.